Okay, I'll give you an overview of robot audition open source software called Hack. My name is Kazuhiro Nakadai, working with Honda Research Institute Japan and also Tokyo Institute of Technology. First of all, I'd like to show you a demo using Hack. This is a meal order taking task using a robot having 16 microphones around the top of the head. Prince Shotoku is a legendary person in Japan who could listen to 10 petitions at the same time. This robot
注文お
tried
願い
to
します。
exceed his capability.
ご注文を伺います。
So 11 people spoke at the same time like this. Using the 16 microphones, a robot localizes each speaker, separates each utterance, and recognizes each separated utterance. If the speech recognition is successfully done, so you can see correct in green characters on your right side.
いいえ。
Okay, then robot completed the task. So of course, this is a champion case. The average success rate is low, like 30%, but this means that speech recognition performance for each speaker is more than 90%. Okay, so my talk today consists of these three parts. I'd like to start with advantages. An advantage of Hack is to introduce a GUI programming environment. It is a web-based environment using Node.js and HTML5. It means that you can make a program with a web browser like Chrome, Safari, or Firefox, both on Linux and Windows. For programming on this GUI, first you need to select these green boxes, which specify functions like sound source localization and separation. Then connect between these green boxes using this black line. And finally, configure some parameters on this property window. It is not so difficult to make a program with Hack, even for non-expert people. Another strength of Hack is supporting many multi-channel sound devices shown in these pictures. However, these products have a risk of discontinuation. Actually, already PlayStation Eye, Kinect, Microcon were discontinued. So we developed a standard microphone array called Tamago, shown here. Tamago means an egg in Japanese. It is sold by System in Frontier for 300 US dollars. As software, Hack does not have any restriction about the layout and the number of microphones. But when you design your own microphone array, you need to calibrate your microphone array. The calibration process is a bit tough, need a lot of measurements, but a YouTube video for this calibration is available, which help you a lot. There are some other advantages. We introduced advanced signal and speech processing techniques, which are robust against real-world situations where dynamically changing and high-power noise sources exist. Hack is user-friendly. For example, installation is very easy. It is okay use apt or apt-get when using Debian-based Linux. Detailed documentation, such as manuals and cookbook, are available both in Japanese and English. And many peripheral packages are also available. For example, you can use ROS together with Hack when you use Hack ROS. And when you want to make your own module, Hack Python 3 here enables you to do it with Python. The last month, we released the latest version of Hack 3.2. In Hack 3.2, we add four modules and packages. HackCN provides distributed processing and make system integration much easier. TFS is still a prototype module, but it will drastically reduce the effort of microphone array calibration because it has a function to adaptively calibrate a microphone array to a target environment. Kibi-based visualization modules add a few types of sound visualization. VAD module provides simple voice activity detection based on a zero crossing technique. So in addition, refactoring of hack and improvement of software stability have been conducted. This slide shows software layers. And actually, orange boxes are included in the hack package. So basically, hack modules use hack middleware, which controls a processing flow. This middleware has a low latency in module integration and is suitable for frame-based integration, which is a requirement for real-time signal processing. Hack also has an interface to another middleware, loss, here. In loss, module integration is a little bit heavier than hack because low score-based network communication is required. But integration with an existing system is easier since ROS is a standard middleware in robotics. This illustrates an example network of hack that is a program of hack. Actually, this is a network of meal order taking demo, which I showed you in the beginning. So it includes sound source localization, separation, and speech recognition. However, it looks little bit complicated. So for clarification, we can reorganize this network in a hierarchical manner like this. So in this case, we can easily understand the function of each part: localization, separation, and speech recognition. I would like to mention distributed processing, which we have recently focused on from the viewpoint of system integration. There are 5 ways for distributed processing. Hack Data Stream Sender is the oldest solution using low TCP/IP communication, and you need to implement a receiver module by yourself. When you are good at Python, Hack Python 3 will be a good option. However, communication between Hack and Python is text-based, so it is not suitable for streaming type of communication. HackCN is newly released in Hack 3.2. Since it supports binary MQTT-based communication and also FLAC-based data compression, it can be applied to streaming type of communication. So this is our recommendation. Hack middleware itself has distributed processing function, but we don't recommend this at this moment since it is not stable yet. When you have a good knowledge on loss, hack loss will be another good choice. In practice 3, you can experience some of these distributed communication methods. I would like to show you an example of distributed processing using Hack Python 3, which was recently published. So Raspberry Pi here and Tamago are connected via USB like this. So this is regarded as an IoT device. And it communicates with a PC here via wireless communication. Sound capturing and source localization is running on Raspberry Pi here. Since no sound source exists, there is no output in the beginning. Then source tracking and visualization processes are started on PC. Now you hear sound, right? So the sound source is started being localized. So you can see the result of sound source localization here, corresponding to this scene. This is another example of system integration using 4 microphone arrays. The system estimates 3D locations and species of birds from the recorded bird songs and reconstructed them into a VR system. So now you hear a sound. It is localized in a 3D way here. Also, the name of bird is identified here. It is red tick. So another one is singing here. So in this case, we directly use a socket interface because the system is a bit complicated. So you can also see the crow flying. So the bird song is tracked. That is sound source tracking. This slide shows Kibi-based visualization modules. Before that, we had only one visualization module called display localization. So it is very fast because it is based on GTK, but it's written with C. It is not so easy to modify it. But Kibi is based on Python. It's very easy to modify the modules. And then anyway, so now we can easily visualize waveform like this, spectrogram like this, and location of sound also. I'd like to move on primary functions of Hack. There are mainly 3 primary functions: sound source localization, sound source separation, and automatic speech recognition. So I'd like to briefly introduce them one by one. Then let's start with sound source localization. Hack basically uses music-based algorithms for sound source localization. Music stands for multiple signal classification, which is proposed by Schmidt in 1986. The original music applies eigenvalue decomposition to a correlation matrix of multi-channel input signal. By utilizing the characteristics that eigenvectors are orthogonal to each other, music can produce a sharp peak in the direction of each sound source, like this figure. That's why music can easily localize sound sources in the real world. However, when noise sources have higher power than the target sound sources, the original music easily deteriorates, like this figure. Because it's very difficult to distinguish between noise sound sources and the target sound sources. To solve this problem, we proposed GEVD or GSVD music based on generalized eigenvalue or singular value decomposition. It takes an additional input called noise correlation matrix, K, which is estimated from pre-captured noise signals. By using K, noise is whitened like this, which makes music much more noise robust. In this evaluation, a sound source with a low signal to noise ratio like minus 10 dB can be localized with GEVD or GSVD, while the original music at most localizes sound sources with 0 dB. This is a movie to show the effectiveness of sound source localization in HERC. We attached 16 microphones to this drone. So actually each microphone is covered with this black fur. So you can see this drone is flying here in this picture. So during flying, a person here sometimes utters. So we first recorded this scene. After that, we analyzed the recorded sound of flying. The reconstructed scene is shown here. When the drone localizes the utterance successfully, you can see a red line here, which shows the direction of the detected sound source. Okay, please watch this movie. So this sound you are listening is recorded by a video camera. Okay? But actual sound recorded by drone microphones is much noisier, like this. So you can see still the drone can detect the sound. Okay, humans cannot detect the sound anymore, but the drone can. So online demo will be presented by Professor Kumon later. This is a general system configuration for sound source separation. Input signals are represented by vector x, and the separated output signals are represented by vector y. Then the separation process is denoted as this equation using a separation matrix W. The main problem for sound source separation is how to estimate this W precisely. So in online processing, W should be updated incrementally like this. Here, mu is called step size parameter, which is usually defined as a fixed value. This means that the step size parameter should be manually tuned. When it is successfully tuned, a mixture of sound can be separated like. However, when it is smaller than the optimal value, the performance drops like this. If it's larger, the separation is diverged like this. To solve this problem, so we proposed adaptive step size control, which makes us free from tuning this parameter. And then we can maintain the performance without tuning like this.
どう
This is a demo recorded when we visited Willow Garage, which was a company developed ROS originally. As shown in this picture, a robot is surrounded by 4 people and they spoke simultaneously. And the recorded sound with the robot microphones is like this.
We're having fun.
All right, so tell me more about this robot. Tell me how
we went
you
over to
all the programming behind
Rudy's
it.
Pub, and it was kind of cool because the whole idea about it was watching
know.
Dallas
Yeah, so
try
you
to
just- you do
sing
the hardware?
country western.
Are you strictly
It was Tuesday.
Yeah, it's really mixed. But after the separation, each sound source is defined like this. This is for Toka 1.
Having fun. We went over to Rudy's Pub, and it was kind of cool because the whole idea about it was watching Dallas.
And this is for Toka 2.
All right, so tell me more about this robot. Tell me how you all the programming behind it, and tell me.
Okay. So it's not so perfect, but it's clear enough. So you can see the video on YouTube also. Okay. Hack provides these 12 algorithms for separation, and items with stars support adaptive step size control, which I introduced before. When we asked what is the best one, we have to say that it's dependent on the situation. But basically, we recommend the last one, GHDSS, that is proposed by us, because this algorithm can maintain the robustness to some extent in various environments. Let me show you examples. This is a result of speech recognition when we used an 8-channel circular microphone array, and there were 5 directional sound sources. The task is to extract one target speech and perform speech recognition for the separated speech. So in this case, the GHDSS, that is our proposal, had the best performance, but some other algorithms also have comparable performance. And this is another example. So in this case, we used a 4-channel microphone array, and we put a diffuser noise. And in this case, so GHDSS still have a very good performance, but it is not the best anymore. Okay, so I have to say the performance is dependent on the situation. You need to choose the best algorithm according to your situation through trial and errors. Then I'd like to move on automatic speech recognition. Hack uses the Kaldi framework for ASR, which is a well-known deep learning-based open source ASR. So we trained its acoustic model for microphone array processing using these corpora such as Wall Street Journal, Libri Speech, and Tedrium. And also we use the speech data after sound source separation as training data. For the microphone array, we selected Tamago, which I mentioned before. Other parameters are almost same as multi-EN recipe, which is provided by Kaldi repository. These two tables show the performance of Kaldi. The upper one shows the performance for clean test dataset of each corpus. So we can see that Cloudy has originally 6% to 10% in word error rate in terms of performance. And the lower table shows the performance with our tuned model with Hack. In this case, the setting was like this. So we put Tamago, which is an 8-channel microphone array here. And we also put two speakers, which are 1 meter away from the microphone array. And these two speakers are 60 degrees away from each other. And from these two speakers, different speeches are emitted with the same volume. Also, we put another diffuse noise here. It's omnidirectional. So in this setting, the signal to noise ratio is always minus. And please look at this table. When the power of diffuse noise is not so big, the performance was like 7% to 13%. Even when signal to noise ratio is 0 dB, the performance is maintained. And as diffuse noise increase, the performance drops like this. So because microphone array processing is based on spatial information, it is good at dealing with directional noise, but it's not so good at dealing with diffuser noise. Finally, I'd like to mention the deployment of Hack by showing some applications. So we started with robot audition, which is located in the center of this figure, and it's expanding to various research fields, such as embedded and vehicle applications, ecology and ecology applications, ICT and cloud services, and search and rescue tasks. So today, as a case studies, Professor Suzuki will give a talk regarding ecology and ecology, and Professor Kumon also give a talk regarding search and rescue tasks. We actually have a lot of videos regarding these four topics, although I don't have time to introduce all of them today. But you can find them on YouTube and the webpage of my lab, Tokyo Tech. In addition, in 2016, a startup company for discussion analysis that is regarding this topic has launched. And this year, the company is about to bloom since they received many awards from Japanese government. This figure shows the history of downloads. The total number is not so big, like 119 kilo, but a good thing is that it is continuously downloaded. So as summary, I introduced an overview of Hack, including the new features in Hack 3.2. And all information can be found in this website. One remark is that Hack is open source software, and you can freely use Hack for research purpose. But license is necessary when you want to use it for commercial use. In such a case, please contact to this email address so they will deal with your requests. When you have any technical questions, please post the questions to Hack Forum shown here. Okay, thank you very much. That's it from me.